Okay, hi there. Welcome back after a bit of a hiatus for another Q&A about science and technology history. So let's see, we had a bunch of questions saved up here. It's a question from Udesio about the history of the computer before the Apple II. Well, one thing you have to understand is computers. The idea of a computer that an individual person would use was something that didn't really arise until sometime in the late 1970s. The original idea, computers that have been built, the first electronic computers built in the late 1940s, and they were things intended for various kinds of research projects, things like the ENIAC, built, I guess, at University of Pennsylvania, and then the JOHNNIAC, the John von Neumann computer built at the Institute in Princeton. Kind of the missions of those computers, which were big room-sized devices, the missions of those computers were primarily various kinds of scientific research or military work. And a common early objective was ballistics computations. If you shoot a projectile and it goes in a roughly parabolic trajectory, it isn't exactly parabolic. It's not as simple as that. There's air resistance, there's rotation of the Earth, there's all kinds of other things. Can you solve the differential equations to figure out where the thing will actually end up? And that was an early use for those kinds of computers. In the early computers, like the one that was built at the Institute for Advanced Study in Princeton, there was a little bit of work that was done on sort of more basic science kinds of questions, like people tried to start working out the digits of square root of 2. Were they going to be random or not? Things like that. And they could have studied cellular automata, a topic I like very much and a topic that John von Neumann also liked. But I don't think John von Neumann ever sort of connected those two things together. And I don't think anybody ever simulated a cellular automaton on an actual computer at that time, or at least not any kind of tolerably simple one. I think there were thoughts back in like 1950. John von Neumann was talking about, could you do weather prediction on an electronic computer? Would it be the case that the equations that describe the fluid dynamics in the atmosphere were easy enough to solve that you could just do them on a computer and get reasonable results for weather forecasts? Before that time, weather forecasting was very much of a pure look at the pattern of fronts and winds and so on, and do things based on sort of the judgment of meteorologists, so to speak. There wasn't kind of a more quantitative side to it. And I think there was a hope at the time. I think von Neumann and Chauny, I think, were the people who wrote an early paper about weather forecasting. There was sort of the thought that, it might just be easy. You might just put in the equations and you might just be easily able to solve them and be able to predict the weather. Turns out it wasn't easy. Turns out weather forecasting is a complicated art that steadily gets better, but there are parts of the world where sort of there are geographic features and so on that make it really difficult to do weather prediction. And there are other places where things are fairly uniform and where you kind of see the weather just transporting across the plains or whatever, and it's much easier to do it. But there's been sort of gradual progress on that, but it wasn't a slam dunk in 1950. As soon as we have the equations on a computer, we can solve it. But so those were sort of some early uses of computers. Then the big one, which had been a sort of pre-use of computers, was for essentially data handling. The original kind of use of punch cards for the census, for example, for the US Census back in the early 1900s, that use of kind of tabulation was something that eventually became databases on computers, but that was a big early use of the mainframe computers that started emerging in the 1950s and early 1960s. But those were kind of early uses for computers, were these kinds of scientific research, military computations, data tabulation, things like that. There were a few other kind of funky uses. Like, I know the early computers made by Digital Equipment Corporation were used to do things like control stage lighting for plays and so on. Those were little so-called, well, I guess, mini computers. I guess that was the PDP, I don't remember which one, maybe 7, 8, maybe, I'm not sure, was used for those purposes. And that was kind of a use that was kind of a separate branch. And I think there may have also been things used for factory control and various kinds of industrial uses like that. But the idea that one would actually have a computer that a person would have, and they would just have their own computer and be able to do things with it, that was not really an idea that arose in the early days of computing, because computers were too expensive, and who would ever do that? Now, there were some things that were kind of little partial approaches to that. That, for example, there was these things on televisions, like I think it was a thing called teletext in England, CFAX maybe in France. I don't know whether there was ever a US system that did this. They were kind of digital information systems that connected to your television, and your television, this was some analog television signals. So it was a radio signal, and the radio signal was specifying every line on the television image. It was specifying, you know, how much black and how much white should be on that line. Later, also color television, but at least when I was growing up in the UK, there were 405 lines in the television image. It then switched to 625 lines. There were these different standards for transmitting signals on televisions. I think in the US it's NTSC. In the UK it was PAL, I think. And the idea of these things was, you're going to send out in kind of a radio signal, you're going to have to say what every frame, every whatever, 15 times a second or something, you're putting up a new image on the television, and you're kind of scanning across these scan lines across the television. And at each scan line, you have to say how much white or black there is at every point. And the thing was that outside of the region where those scan lines existed, so you'd scan down the whole 405 lines down the television screen, but then before you needed to start retransmitting the next frame, there was like a couple of scan lines worth of extra sort of bandwidth to use. And so the idea was, well, let's have some kind of digital information system that would be able to pick up the data from those extra scan lines. And you'd have this thing where you would say, okay, there's 500 pages of information that's being continuously updated. And you would click through to say, I want page 200 or something. And then it would gradually fill in page 200 as it found the data for page 200 from the scan lines that it was using from the television signal. And so that was sort of an early place where people saw something that looked a little bit like a computer screen on their television, so to speak. And when was that? That must have been late 1960s, I think. Well, then this idea, I'm trying to remember all the different branches of kind of the emergence of personal computers. There was the Sinclair ZX80, which was a kit computer. A lot of the early kind of have a computer for yourself were kits, which were intended for hobbyists of various kinds. There was also there was also much later, that must have been much later, the BBC Micro, which was a big project in the UK to sort of get computers out in the world. I think that was significantly later than that. In the US, there were companies like Altair, and there was a whole sort of gaggle of people around the Homebrew Computer Club that met in the Silicon Valley area. At the time, the Silicon Valley area had companies in it like Varian Associates, which was a radar company that came out of kind of work done in World War II. And also, I guess, Hewlett-Packard was there as well, making primarily scientific instruments of various kinds. There was sort of a slightly emerging tech scene there. And the Homebrew Computer Club was one of the kind of fixtures there. And I guess I've met lots of people who were involved in that enterprise when it was going, and that must have been the mid-1970s. And sort of out of that and this tradition of kit-type computers, I think there was, if I remember correctly, there was some kind of hub of companies that did that kind of thing in Albuquerque, New Mexico. That was Microsoft's first location. Microsoft's first product, I think, was a BASIC interpreter for, I think, one of the Altair computers. But in any case, so that sort of the early tradition had been, if you want a personal computer, make it yourself. It's kind of something that you would assemble from a kit, and people would kind of exchange plans for how to do this, and you would buy the components and put the thing together. Kind of one of the things that came about with Steve Wozniak and Steve Jobs is Apple computer was this idea that it's sort of a pre-assembled thing that you could just get. I think there have been other examples of that as well, but there was definitely an emphasis on sort of the kit idea. I think the original Apple I computer had a lot of kind of interesting, strange marketing ideas. I think its original cost was $666, which turned out to be not so felicitous in terms of the sort of kind of biblical legends around the number 666 and so on. But by the time then there was sort of a question, the kind of the objective was, could you actually make a computer that people could use? What kinds of software will people run on it? Those were some of the early kinds of things. I have to say, I didn't use personal computers at that time. I used, I think the first computer that I personally owned was probably an Osborne 1, and that must have been in 1980. When was that? Probably 1981 or 1982. That was an early portable computer that was the size of a small suitcase, and it plugged into the wall, and it had a little CRT display, and it had a couple of floppy disk drives, and it ran an operating system called CP/M, which was the typical early operating system of these kinds of personal computers. And it was, you could use it for word processing, and I used it a few times, but honestly, I didn't find it that useful. I had the interesting experience of trying to actually use it as a portable computer, and that was, it wasn't the suitcase size, it wasn't that portable. But for me, for example, at that time, I was using computers that were more kind of the size of half a room. They were computers like the, well, either computers that were more of the sort of scientific mainframe class, like CDC type computers, or later computers made by Digital, the VAX 11780, which was a computer about the size of, well, it was a big computer that needed to be in sort of a special room, and it kind of stood about 5 feet high or something, and it was a big metal cabinet that was maybe 4 feet deep or something, and it was a kind of a long, I don't know, 15 feet long or something like that, and it was kind of it had that was a computer that had a few megabytes of memory, and it had big disk drives that could store a fair amount of memory, and it was a computer that had the ability to run programs that were bigger than the physical RAM by using virtual memory, by swapping data out onto disk and so on. So I have to say, I was not as aware of kind of really personal computers until, well, quite a bit later. I suppose the first computers that I kind of used as a kind of computer to be the only user of were Sun workstation computers. That must have been in 1983 or so, 1982, 1983. Those were computers that were about, they were sort of well, they had a big bitmap display, and they were kind of, oh, I don't know, how big are they? Maybe maybe the size of a stack of about 5 or 6 pizza boxes or something. Was the typical. Actually, some of them also had sort of boxes that stood on the side, but those were kind of the first computers that I used as kind of serious, I'm the only user of this computer computers. Actually, yeah, I think I first saw one of those computers. Well, I can tell you quite a bit about the history of those kinds of computers, because I was quite involved in that, because we had built software, our SMP system that was kind of released in 1981. One of the great interests was getting it to run on all those kinds of computers. So I interacted with most of the companies, I would say, that were building those types of computers around that time. Well, let's see. Oh, we got lots of new questions here. Let's see. There's a question here from Karup about what is the fine structure constant and why was Dirac so interested in it? Well, okay, so fine structure constant, usually called alpha, has value about 1 over 137 point something or other. The fine structure constant is most interesting in the way that it characterizes the strength of electromagnetic interactions. So if you have kind of a, it's kind of a dimensionless number that characterizes sort of how strong the forces associated with electrical processes are. And it's something that originally arose in things to do with observing atomic spectral lines, the absorption and emission of light in discrete frequencies by atoms, and the fine structure constant arose in the kind of splitting of lines that might otherwise have been a single spectral line. A single frequency was split into multiple frequencies by an amount that was characterized by this fine structure constant. But the thing that's important more fundamentally about it is in quantum electrodynamics, originally the theory of electrons and photons, the theory of processes that just involve the electromagnetic field, the electromagnetic forces, and so on. That is the thing that characterizes kind of what essentially the likelihood that an electron will produce a photon is, or the likelihood that a photon will interact with an electron. And so when one sets up Feynman diagrams, this kind of diagrammatic mechanism invented by Dick Feynman back in the 1940s, as a way to represent kind of the interaction of electrons and photons, you can say, well, I've got an electron and it's going to have an electric repulsion from another electron. Well, how does that electric repulsion actually occur? Well, in quantum field theory, it occurs by the exchange of some discrete number of virtual photons. So each electron, in a sense, virtually emits a photon, which then virtually is absorbed by the other electron. And that photon is essentially transferring momentum from one electron to the other. And so making it to exert a force on the other electron. And you can kind of work out the full kind of effect of electromagnetism as well as the exchange of one photon. There could be the exchange of 2 photons. There could be exchange of 3 photons and so on. And the chance of exchanging that photon is determined by a whole bunch of mathematical computation, but everything's multiplied by alpha, the fine structure constant. That characterizes the chance of emitting, absorbing, exchanging a photon. And so the chance of exchanging 1 photon is proportional to alpha, 2 photons proportional to alpha squared, 3 alpha cubed, and so on. And so it tells one that when one tries to do computations in quantum electrodynamics, because alpha, 1 over 137, is a pretty small number, there's at least a decent chance that you can just look at the exchange of just a few photons to get a pretty good estimate of what the complete amount of electromagnetic effect is in some particular system. that's a complicated story because it's known that the series isn't just alpha to the power k times some kind of fixed size number, but the coefficient can increase like square root of k factorial in kth order. And there are other situations in which the real expansion parameter is not alpha, but pi squared times alpha, and pi squared is 10, and so it isn't quite as small. But roughly, alpha is the thing that is sort of the expansion parameter in the power series of working out the effects on quantum electrodynamics. Okay, but if you want to sort of understand kind of where does quantum electrodynamics come from, what is the kind of fundamental source, what is the more fundamental theory which could lead to quantum electrodynamics, it's a good target to say, well, there's this number in quantum electrodynamics, about 1 over 137. Let's try and reproduce that number. And in our theory of physics, for example, eventually we should be able to reproduce that number. But nobody really knows at all right now why that number has the value it has. There's a little bit we know because that number is the number you get from essentially low energy electrons, low energy photons being exchanged between electrons. If you say, I have a photon and it has a very, very high energy, very high momentum, 4 momentum squared, whatever, very high, okay, so photons, the energy of a photon is proportional to its frequency. Photons of visible light have a frequency of around terahertz and a bit more than that. And photons of radio photons have maybe megahertz to gigahertz, million cycles per second to a billion cycles per second. When you get to things like X-rays and gamma rays, the frequencies are much higher, and the resolution that you can the kind of, if you made a microscope or telescope with a particular frequency of photon, what comes from the resolution that you can get with a photon of a certain frequency depends on the wavelength of that photon. And so as you get to higher frequencies, higher energies, you get to correspondingly smaller wavelengths, and so you can effectively resolve smaller things. So you can think of kind of various kinds of particle accelerators as being like things that produce, well, kind of virtual photons. So it's a little bit of a different story, that are very high energy, very high frequency, very short wavelength. And it's that kind of short wavelength that allows them to kind of resolve features of things on a smaller scale. So right now, the highest energy kind of resolution is around 10 to the minus 19, 10 to the minus 20 meters, something like that. But kind of the point there is that as you get to higher, sort of that smaller scale of resolution, okay, there's a tricky thing. Maybe I can try to explain it. It's a piece of physics that has to do with this thing called the renormalization group. And here's roughly how it works. So if you imagine, let's see how best to explain this. When you think about an electron, the electron always has these photons being emitted and reabsorbed all the time. There are virtual photons being emitted and reabsorbed by any electron anywhere. In fact, in the nominal way that you compute how often that happens, it happens infinitely often. But the kind of trick of renormalization is to say, well, a bare electron, we don't know what a bare electron looks like without any of those photons coming out and being emitted and absorbed and so on. All we know is what an electron of the kind that we see, which includes all those photons being emitted and absorbed and so on, looks like. So even though there might be an infinite effect of those things, the bare electron might be infinitely different than what we see, and all we see is the difference between those infinities, which is the actual electron we see. But around every electron, then, there's this kind of virtual cloud of photons and electron-positron pairs and all kinds of other things that are being produced, emitted, and absorbed over very short periods of time. And as you kind of try to home in and look at the electron in more and more detail with essentially a higher and higher energy photon, you get to sort of drill in and see into that kind of cloud of stuff. And you get to sort of get closer and closer to the bare electron, so to speak. And so that means that the effective properties of the electron will actually vary with essentially the energy, the wavelength, the resolution of the probe that you're using to probe the electron. And so one of the things that varies is this is essentially this alpha parameter, which is essentially the so-called coupling constant, the strength of interaction. When you look at the electron very, very close up, it will seem like it has a stronger strength of interaction than it does when you look at it at a greater distance. And so that is called the presence of a so-called running coupling constant, the fact that when you look at higher energies, you're kind of drilling deeper into, you're looking at higher and higher resolution, and the electron looks as if it has a higher charge effectively as you probe deeper inside. You can roughly think, it's not quite right, but you can roughly think, oh, there are these things that kind of screen out the charge of the electron, and you're kind of looking inside that shell of screening to see kind of a higher charge, and there's kind of a logarithmic variation as a function of essentially the energy, that is a change of the effective coupling constant. Okay, so for quantum electrodynamics, the effective coupling constant increases as you probe to higher energies. One of the important things about quantum chromodynamics, the theory of quarks and gluons, is that it goes the other way around. There's this phenomenon called asymptotic freedom that was discovered in 1973, in which it turns out that for quarks and gluons, when you probe at higher energies and at smaller scales, the effective coupling constant actually seems smaller rather than seeming larger. And that's very important in the ability to actually do computations in QCD. I had lots of fun in the late 1970s doing such kinds of computations, because you can, as soon as you're sort of probing things at high energies, the effective coupling is small enough that you can use Feynman diagrams and just compute sort of terms in a power series to get estimates of what's going on. But in any case, back to what that means for alpha, the fine structure constant. It means that the fine structure constant, 1/137, that's its low energy value. The fine structure constant actually runs to larger values as you increase the energy. And one of the things that people were very excited about at the end of the 1970s, early 1980s, is if you kind of track the running coupling constant of quantum electrodynamics and the running coupling constant of QCD, the two things kind of converge. So it's as if there's sort of a unification at around 10 to the 15 GeV that 10 to 15 EV actually. Is that right? Oh boy, it's been a long time since I thought about these things. Yeah, I think it's 10 to the 15 electron volts. So that's at that energy. So that's a million, the equivalent of a million proton masses. Is that right? That, let's see. I might be off by a few orders of magnitude there, but sorry, it's a long time. I used to write papers about these kinds of things. I think I last wrote a paper about these kinds of things and their relationship to cosmology in 1980. And that neuron may not be with us anymore that has that data. But in any case, the main point is that these coupling constants, as you increase the energy, they eventually get to be the same value. And people thought that was very significant. And that was a sign of some sort of unification, that all these different forces of nature, so to speak, all these different types of interactions were really the same thing. And it was just because we're kind of looking at them at low energies that they appeared to be different and have different effective coupling constants. So that explaining the 1/137 is a little bit of a trickier thing, because it really is only 1/137 in this low energy limit that we happen to be used to looking at. Okay, so there's a history of people trying to explain how 1/137 arises from some more fundamental theory of physics. There was a chap called Arthur Eddington, who in the 1920s and 1930s, I think, was very big on finding sort of a a fundamental theory of physics. He was also the person who famously went to do the observation of a total solar eclipse in South Africa in 1919, I guess, that validated Einstein's general theory of relativity by looking at the additional bending of light around the sun predicted by that theory. How accurate that, how good that experiment really was is not particularly clear. I think there was a certain degree of a desire to find a certain result in that experiment. But anyway, Arthur Eddington's kind of more day job was studying sort of theoretical aspects of physics. He was based in Cambridge in the UK, he famously had this kind of fundamental theory of physics that would just involve numbers and kind of explaining everything about the universe just by working things out as a sort of number theory exercise, though number theory itself wasn't very popular in those days, and I don't think he described it that way. But famously, he got the result 1 over 136 for the fine structure constant. And at the time, 1 over 136 was the experimentally observed value of the fine structure constant. So it's kind of a pattern here of why I'm a little bit suspicious about the 1919 observation and so on. Because then what happened is that the experiments were done more accurately and the number really kind of flopped over to being 1 over 137. It looked like it might be exactly that as a reciprocal of an integer. Turns out it wasn't exactly that, but that wasn't known at the time. And so famously, Eddington said, oh, he made a mistake in the calculation. You need to add 1 for the trace of the matrix. The result really should be 1 over 137, which just wasn't very convincing because it was one of these things where, first it had been 1 over 136, then 1 over 137. Okay, why was Paul Dirac interested in these things? Well, Paul Dirac was most famous for the Dirac equation and for having predicted the existence of the positron, the antiparticle of the electron. So the Dirac equation originated in the 1920s, I guess, and was along with kind of the general origination of quantum mechanics. In quantum mechanics, sort of the first thing that was a very kind of quantitatively explorable thing was Schrödinger's equation. When Schrödinger had this equation that describes the wave function, so-called wave function, that is then interpreted in Max Born's Born interpretation. The square of the wave function is the probability, and when you make a measurement in quantum mechanics. But the big point of the Schrödinger equation is that it's an equation that looks very much like the diffusion equation, like the equation for sort of the diffusion of a gas, except that it has an I in it, a square root of -1 in it. So it's like an imaginary complex diffusion equation that describes how this kind of a wave function that represents, in the end, the probability of finding a quantum particle somewhere is going to evolve with time. Or in particular, if you have a stationary state, like the analog of having, a string where you have the string fixed at the ends and you're just sort of bowing the string, you're playing a string. There are certain modes of the string, from the string has just sort of one peak in the middle to having 2 peaks, 3 peaks, and so on. Those kind of eigenmodes, those sort of things which are the consistent possible solutions to the equation given those boundary conditions, given that you've sort of anchored the string at the 2 ends. The analog of that for the Schrödinger equation is things like solving for what will an electron do when it's trapped inside a hydrogen atom, when it's trapped by electrical forces inside a hydrogen atom. What will an electron do? And so solving the Schrödinger equation for that, you can do that and you get out this whole thing involving Laguerre polynomials and all kinds of other nice mathematical constructs. But the end result is, just like you have these discrete frequencies for a plucked string, so you have these discrete energy levels for electrons in a hydrogen atom, and those were found to be more or less as people observed them. But one of the things about the Schrödinger equation is it describes the probabilities, probability amplitudes for non-relativistic particles, for particles that are going slow compared to the speed of light. But then the question was, well, how would you combine relativity, special relativity, and quantum mechanics? How would you combine those together, how would you deal with particles which were not going slowly compared to the speed of light? And that's where Paul Dirac came into the picture and came up with the Dirac equation, which is an equation of a somewhat different form that has the feature that if you have low velocity particles, it's just like the Schrodinger equation, but if you have higher velocity particles, it works differently. And it's an equation which ultimately describes electrons, relativistic electrons. And it was an equation that has the feature that it has both a positive energy solution, and the equation has a sort of symmetry in it, which means that in addition to the positive energy solution, there's also a negative energy solution. And Dirac wasn't sure quite what to make of that, and realized in the end that one should think of that as being the existence of an antiparticle to the electron. It's a little bit more complicated. One thinks of this kind of sea of electrons, that sort of the filled sea of electrons, and then there's a question of there will be a sort of a hole in that filled sea that represents the positron, the anti-electron. So the anti-electron has a negative electric charge. It still has a positive mass. That's described by the Dirac equation. And the Dirac equation, that was sort of the thing that Dirac was particularly famous for, was the Dirac equation and the prediction of the existence of the positron that was observed in cosmic ray experiments in early 1933-ish, I think, was actually found to be a real thing, just like the electron, but was with opposite charge. So Dirac was interested in other kinds of things. He was very much of a purist, very much of a kind of minimalist physicist. I never met him, unfortunately. I could have done so, but I did not do so. My friend Dick Feynman always used to say that one of the features of Dirac was that he would always give just one-word answers to any questions. He was very, very kind of cut and dried monosyllabic. I think he also was very much more that way when he lived and worked in Cambridge in the UK. When he finally retired, Cambridge had a mandatory retirement age. When he finally was sort of retired from Cambridge, he went to work in Florida. And apparently he really opened up when he went there and became kind of a quite social, cheerful fellow who would chat with people, which he really hadn't been doing at all in the past. But in his later years, Dirac was interested in the possibility that things like alpha, the fine structure constant, might be things that varied during the history of the universe, and might be things where, as the universe expands, for example, the value of that might change. People had thought from people like Ernst Mach, Mark's principle and so on, that maybe the whole of the universe has an effect on, for example, that inertia might be a result of the effect of the whole of the rest of the universe on us here. I don't think that's quite the right way to think about it, but that was a sort of an idea that was kind of in the air. And Dirac had this notion that maybe the fine structure constant changes over time, and there will be consequences to that. Like, for example, the size of the sun, the size of the earth would potentially change because the sizes of atoms would change because of that. And Dirac tried to look for evidence of those kinds of things. And that was something that I know he was interested in. I don't think there is evidence of that. I personally would be surprised if, based on our current ideas about fundamental physics, I would be surprised if in the current epoch of the universe, if there's a change in the fine structure constant as a function of time, as a result of kind of cosmological effects in the universe. In the very early universe, I think it will be a quite different story, but I think everybody thinks it would be somewhat different in the very early universe. Let's see. Oh, there's a question here from Irish asking, can you recall any what could have been moments in the development of computers that could have taken off had the right decisions or factors occurred? Well, there are so many things. I mean, you know, I think one of the most dramatic probably was in the 1840s. Charles Babbage had this design for his analytical engine, which was a mechanical computer. He had built a difference engine, which was a way of essentially computing values of polynomials by using this complicated gears and cogs type machine that was actually built. He had this plan for an analytical engine, which would use punch cards of the kind that Jacquard had invented back in 1800 for controlling looms for weaving and so on. The idea was that that would control the operations of the computer, of the analytical engine. Everything in those days was an engine, so to speak, because steam engines were really big in those days. And so that was something where Babbage had kind of this design for how you could sort of specify an arbitrary computation using these punch cards and having all this gearing and things to do different operations depending on what the punch card said. And that would have led to, the idea was to make this thing kind of the size of the size of a steam engine, actually, that would be this sort of giant analytical engine. Okay, so the idea was make an analytical engine, you'd be able to do all kinds of computations. Babbage was not a particularly good manager of large engineering projects. And he also was quite obsessed with getting other people to pay for things, even though he probably could have actually paid for things because he'd inherited a lot of money from his father, who was a banker. And then he later was involved in a startup, which was a insurance company that I think did quite well. But anyway, he was much more concerned with getting the British government to pay for things, and they paid for a bit and then wouldn't pay for more. And he had this friend, Ada Lovelace, who was significantly younger than him. They met, I think, when she was maybe 17 and he was like 40. And Ada Lovelace was I think she really saw herself as much as anything as a potential expositor of science. She kind of had as a bit of a model Mary Somerville, who'd been a translator of Laplace's celestial mechanics works, I think, and also a person who'd written a lot of science exposition. And Ada Lovelace was the daughter of Byron, the poet, although she never met him. And I think had sort of a proclivity for writing. But in any case, she got very interested in the difference engine and later in the sort of plans for the analytical engine. And in the end, when Babbage was sort of describing the analytical engine, he wrote one kind of paper that was originally in Italian, I guess, that was a description based on some lectures he gave of the analytical engine. And they were going to be republished in English. They were translated by a chap who was in the Italian kind of Corps of Engineers, later actually became the Prime Minister of Italy. That person did. Menabrea was his name. In any case, he translated this, and Ada Lovelace took it upon herself to write an introduction to the piece about the analytical engine by Babbage. And the piece about the analytical engine by Babbage is a very engineering kind of document. Ada Lovelace tried to describe a bit more in a sort of broader terms what the significance of the analytical engine might be, and managed to figure out a lot. I mean, she really understood kind of the abstract idea of computation, which I don't think Babbage ever did. I think he was very much, let's use this thing to print mathematical tables, that's what it does. And Ada Lovelace had this very nice place where she says, the algebraical engine, the analytical engine will, just as the Jacquard loom can be controlled by a punch card to weave patterns of birds and flowers, so the analytical engine will be controlled by punch cards to weave algebraical patterns, which might include things like algorithmically, she didn't use the word algorithm, composed music, and as well as mathematics and other kinds of things. So she had pretty good idea of kind of this general notion of computation. Meanwhile, Babbage was trying to get the analytical engine built. He was trying to get Ada Lovelace, who he thought was much richer than him, although I don't think it was true in the end, because I looked at his account books. I think he was, all his life was under complete misimpression that because Ada Lovelace was a countess, she must be much, much wealthier than him. He was a mere, son of a banker type thing. But in any case, this was, he tried to get Ada to be kind of a fundraiser and to go convince the British government and Queen Victoria and people like that, yes, the analytical engine should be funded by the government. Well, in fact, what Ada said to Charles Babbage was, look, if we're going to make any progress with this thing, you got to let me, Ada, run the project. You're just totally incompetent at running this project. And there's a wonderful series of letters that the two of them exchanged, which I had a chance to look at a number of years ago. Back in those days, there were like 14 mail deliveries per day in London, and they also had people who would deliver mail between each other. So they were doing the equivalent of exchanging almost text messages. And so you see this going back and forth in the archives that are still there of Ada sending Charles Babbage this letter that basically says, you got to let me run this project if it's going to go anywhere. And Charles Babbage writes on the letter, I refused all her demands. But then a few hours later, he's kind of recanted and eventually says, sure, you should run this project. Well, unfortunately, Ada Lovelace got sick, probably with probably cervical cancer, and that sort of took her out of action. And so that never really happened that way. Had it happened, what would have occurred in the history of computing? Probably the analytical engine would have been built. Probably it would have been used to compute, well, all sorts of things for astronomy, for navigation, for life insurance tables. It would have been kind of a Victorian cloud computing operation. And that was kind of the idea that Ada Lovelace and Charles Babbage had, was kind of that people, it would be a service bureau where they would operate these giant analytical engines. One can sort of imagine them in London. I think at the time, they very much imagined them as mechanical devices, although they were acquainted with people like Charles Whetstone of electrical and Michael Faraday also. And so there was kind of some knowledge of electrical devices as well, and perhaps they would have made the jump to electromechanical devices instead of pure mechanical devices. So that's definitely one moment in the history of computing. The 1840s might have been the early cloud computing, a very loud electromechanical cloud computing, but it might have been a kind of early use of that. And it might have been the case that the things that Ada Lovelace figured out about kind of this abstract theory of computing might have taken off at that time. As it was, they were kind of lost for 60, 70, 80, more than that years, nearly 100 years actually, and nobody paid attention to them. And that was kind of not the path that things went on. So that was one kind of history of computing, might have been a different way. I think another one, by the time kind of the origination of kind of our modern ideas of sort of universal computation started coming around, first with Moses Schoenfinkel in 1920, then with Kurt Gödel in 1931, Alan Turing 1936, Alonzo Church 1935, all these kinds of things coming in, all these different models of the computational process, all abstract models being invented essentially for the sake of doing mathematics and doing logic. I think by that point, there was not too much that was dramatically missed at that time. Perhaps the one thing that was missed was combinators, invented by Moses Schoenfinkel in 1920, the SK combinators, which are things that were sort of the original kind of way to do arbitrary symbolic computation. They're very obscure. You have this whole combination of S of K, of S of S of K, of K of K, whatever, big long strings of S's and K's, and you feed them a symbolic argument, and then they have reduction rules, and you can do any computation with those reduction rules. I studied this a bunch towards the end of last year in preparation for the centenary of combinators on December 7th of 2020. But combinators are this way of computing that involves having symbolic expressions and making transformation rules for symbolic expressions. very different from the way of computing where you say, I've got a small collection of numbers which are stored in registers, and I'm going to sort of do arithmetic operations on those numbers. It's a much more abstracted, much more symbolic version of computation. It's one that I made significant use of when I started designing first SMP and then Wolfram language back, well, 40 years ago now. But combinators are this different model of computation that are still pretty hard to understand in their raw form. Had people understood them back in 1920, and it would have been a huge challenge to understand them really at that time, because the whole context wasn't really up and running at that point. Had people understood them, they might have built computers in an utterly different way. And for example, they might have realized, as we still don't know how to do, how to make molecular scale computers that really can operate with molecular components. That's something I think much more plausibly to come from studying things like combinators than to come from studying collections of numbers and registers containing numbers and so on. Now, another sort of might have been a different way is that Moses Schoenfinkel himself was presented this one lecture about combinators in 1920. And then in 1924, he'd been in Göttingen working around David Hilbert, a famous mathematician, although Schoenfinkel himself came from Ukraine. But in 1924, and we've tracked down the exact day when this happened, Moses Schoenfinkel went to Moscow. We still don't know really why. And Moses Schoenfinkel disappears from view after that time. So no idea what happened to him. There are sort of rumors that he had various psychiatric issues, although the evidence for that is not overwhelming. But in any case, Moses Schoenfinkel sort of disappears. Had he not disappeared, had he built a whole giant kind of career out of studying combinators, it's possible that the history of computing would have been somewhat different, and that we would have seen symbolic computing and functional programming and things which are both features of combinators much earlier. Now, Haskell Curry, who kind of picked up on combinators, did not independently discover them. He'd been kind of nosing around the same area. And then in 1927, he found found Schoenfinkel's paper in the Princeton University Library and embarked on a whole career of studying combinators. Although I don't think he really understood some of the deeper significance of combinators as foundational ideas for computing. I think he really thought of them more as something that you did logic about. Well, actually, that's kind of what I thought was the case. But I've heard from people that actually Haskell Curry, when it was first, was actually quite involved during World War II in various kinds of early computer efforts, and later in things related to the ENIAC and so on. And that he actually, I have heard it claimed, I don't have great evidence for this yet, that he had actually proposed on the basis of, of his study of combinators and also of the somewhat more understandable lambda calculus from Alonzo Church, that really computers should work by what amounts to functional programming. But he wrote these reports and people just ignored them. And John von Neumann, who wrote the more famous reports on kind of how computers should be set up, really was pushing the write it like standard kind of the way we see low-level programming languages work today, where there are variables and numbers and arithmetic operations on numbers and program counters and jumps and loops and things like this. Apparently, Curry, sort of basing it on combinators and a little bit on lambda calculus, had proposed something much closer to functional programming, but it didn't happen that way, probably because people didn't understand what he was talking about at the time. I mean, I know that, another thing around the same time, Ken Iverson developed APL as kind of this notation and language for doing array processing, another functional programming language, originally developed more as an on-paper language than a thing that was actually going to be implemented on computers, although it was implemented on computers. Ken Iverson kind of made the mistake of having this sort of special weird character set that would be sort of the math operations of algorithms in APL. And APL just didn't catch on, really. It caught on a little bit in some particular parts of the financial industry. Morgan Stanley, for example, used it quite a lot, and so on. And I think that that was another kind of near miss of APL not catching on, and instead, for example, BASIC, which was much more a sort of a simple language based on the kind of very much von Neumann kind of variables and loops paradigm for programming, was something which was used along with Fortran and COBOL and so on, which were again in that tradition. There was also the Lisp tradition that was from John McCarthy in 1958, and that had kind of come out of Church's lambda calculus, and again was something which was not very widely understood, and it also had the problem it was really hard to implement back in the early days. In fact, even when I started writing systems for doing symbolic computation, this is now late 1970s, it was not realistic to use Lisp. There were systems that were based on Lisp, but it was quite impractical. It just wouldn't run fast enough on practical computers at the time to be used as a foundation. And although it had certain aspects of it were mathematically elegant, sort of interesting what happened. There was a certain elegance to the lambda calculus part of it, but then there were things that didn't quite work, that involved kind of variables and the renaming of variables when you have nested lambda functions, things like this. And it's like, then there started to be these hack towers. And there were these things about how you actually did reduction of lambda expressions, and what in lambda calculus would be beta reduction and eta reduction, all these kinds of things. How would that really work in the context of a practical computer system? And I would say that there was a certain degree of kind of rising tide of kludgery that was needed to make all that stuff work, which kind of downgraded the otherwise very elegant kind of conceptual foundation of what was done with Lisp. So those are a couple of things that I suppose functional programming could have come in much earlier. The whole idea of computing could have come in much earlier. We could have had a very different foundation for the way that we currently think about computing. I mean, those are a few things. Another thing that there are so many of these. I mean, there are so many detailed things where there were sort of technology competitions between different technologies, and where the technology that won for reasons that had to do with either a detail or a business situation, all those kinds of things that were almost coincidental to what one might think of as the kind of intellectual thread of the development of computing. All right, there's a question here, another what if question from David. What do you think would have happened if Archimedes had discovered calculus in 200 BC? Interesting question. First question is, what would he have used it for? Because I think in Greek times, the notion of kind of things happening as a function of time, which is a large part of the story of calculus, wasn't so much there. It was, what's the universe made of? Okay, it's made of atoms. Okay, maybe it's made of different kinds of polyhedra put together. Okay, maybe there are epicycles, and these epicycles are crystal spheres, and they have this certain configuration of motions, but it's very much of what's the thing that's there. It's not how does something change over time. The idea of sort of change over time, I think, came in much more, by 1200, 1400, people were kind of vaguely talking about almost making sort of space-time pictures of things, of showing things as a function of time, so to speak. And then Galileo, for example, was I think very much more into that as he started talking about motion and discovering kind of the parabolic law for position as a function of time under uniform acceleration, for example, in the Earth's gravitational field. And then by the time Newton was in the game in 1687 and so on, that was a time when people were really understanding that we want to study things happening through time, motion happening through time. And I think that was a thing that was for Newton, probably, that was the story of calculus. Newton talked about fluxions, now our x dot notation and things. That was all about things fluxing, things changing in time. I just don't think that notion really was something that Archimedes was as into. I think Archimedes was more into the sort of the static shapes of objects. So the discovery of calculus that happened with people like Newton, that is really, I think, a story of people being interested in the development of things in time. Now, could Archimedes have discovered calculus as a way to do mensuration, to do the measurement of, for example, solid objects? Archimedes had some pretty good tricks about figuring out, the volumes of cones and compared to spheres and things like that. He'd figured out pretty well how to work out the kind of the volumes of things. And I don't think he had a great need for calculus in doing that at that time. I think he'd gotten good enough with his geometrical kinds of methods to not need that. Now, subsequently, people like Kepler, this is way later, this is 1600s, Kepler was interested in things like the volumes of solids of revolution. I think Kepler had a little side business computing volumes of wine casks based on their external shapes. And that was something that needed sort of a pre-version of calculus. So I think Archimedes wouldn't have known what to do with sort of time-varying calculus. I think he might have known what to do. He might have been very excited about, oh, I can now work out the volumes of these figures using calculus rather than using these geometrical tricks. But I don't think that, for example, Newton's laws of motion, I don't think that people were kind of ready yet for thinking about those sort of time-dependent phenomena at the time of Archimedes. I think that now, in terms of something which, another what if of computing, the Antikythera device, this device that comes from around between 100 BC and 100 AD, this a single object that we have from antiquity, which is a collection of gears and so on, that is essentially an astronomical mechanical computer that has some number of tens of gears in it. It's pretty elaborate computations that it's doing, including things like estimating when eclipses might occur and things like this. That was a device that I at least sort of romantically think might have been made by or involved with Archimedes. And I think that an interesting question is, maybe Archimedes had a side business that's a little bit like our business of making tools for mathematics, so to speak. And they might have been not the calculus tools, but mechanical tools. Somebody had to make the Antikythera device, and there probably wasn't just one of them in antiquity. And there's sort of a question of why didn't that tradition of sort of clockwork computer-like things survive from antiquity? And had it survived, how would the history of computing be different at the present time? But I kind of think that Archimedes wouldn't have known what to do with calculus if he had discovered it at that time. At least that would be my initial take. Okay, maybe one or two more. Let's see. Well, question here from Monopoly. Do you agree with the people that physics and science has made minimal progress in the last 25 years compared to before? All this progress has all slowed down. It's kind of funny because I have friends both who say there's about to be a singularity, there's exponentially increasing progress, and other ones who say, oh, there's nothing new under the sun, all progress has slowed down to a crawl. How can they both be right? Well, there are things like the number of academic papers being written, that's increased. I don't think that's a great measure of anything. That's just a measure of the number of people who are getting paid to do science and the dynamics of that sort of institutional mechanism. I think the thing that is very confusing is the following. In terms of sort of the rate of expansion of knowledge and science and so on, is this. When there's something new on the scene, new methodology, new area of inquiry, new set of tools, when there's something new on the scene, there's a whole bunch of low-hanging fruit to be picked, and things happen quite quickly. But when it's all been picked, things then happen quite slowly. Now, depending on the field and the magnitude of the sort of tools and so on, that period of rapid growth may be a variable length. Sometimes it'll be 5 years, sometimes it'll be 10 years, sometimes it might be 25 years, sometimes it may be even a bit longer than that. But it's a finite length. And after that period of rapid growth is over, what you typically see is a long grind for 50 years, 100 years, before perhaps some particular area of inquiry takes off again with some new methodology, new tools, and so on. So, for example, in physics, back in the heading towards the early part of the 1900s to 1920s and so on, just tremendous growth. A lot of new methods, new ideas, new mathematics led to relativity, quantum mechanics, etc. And then again in the 1970s, particularly in particle physics, rapid growth. But I was involved in that rapid growth period in the 1970s in particle physics, and it was a period of, I don't know, 6-7 years, when it became clear that you could use a bunch of methods from quantum field theory to do things, and there was a lot of interesting stuff to figure out. And by golly, in 6 or 7 years, with a whole bunch of people working on it, a bunch of it got figured out. And then all the easy stuff was done. And then it was a long grind of doing much harder stuff. And that's very typical in all these different fields. So for example, in recent times, we've seen machine learning go through this cycle. Machine learning had kind of originated in, I suppose, the neural net idea in the 1940s. It had various little bursts of activity in the 1960s and the early 1980s, hadn't really worked out that well. Then suddenly, 2011, 2012, bursts of interest in deep learning, things really take off. And there's a lot of low-hanging fruit. There's a lot of things that can be done, given that new methodology, comparatively easily. After, people are rushing to do it and lots of interesting things get done. And then the easy stuff gets done. Those become sort of pieces of methodology that sort of go into a more engineering kind of mode. And now it's getting hard. And so that field, you could say, well, machine learning, it's proving that nothing's going to be new in the world because machine learning is slowing down. Well, that's because it had its rapid growth phase because there was a really new and important methodology. One of the things exciting to me right now is with our physics project, we're seeing kind of a growth of what's possible in physics that I don't think one's seen in, well, close to 100 years, actually. I think that what one's seeing is a new methodology, new set of tools, a new kind of paradigm for making models of things. I'm only just understanding that part about the kind of really new paradigmatic approach to model making, but that's allowing one to sort of have this rapid growth, which I think we're in the kind of just about year one of right now, of things that can now be done in physics. And actually it goes beyond physics. This kind of paradigmatic approach is something that applies to a whole bunch of other fields too. It's kind of a new approach to modeling things. I will say that I've kind of been developing this view of kind of the evolution of modeling in science that really has 4 phases, 4 epochs. The first epoch being in antiquity, when the realization was that, gosh, this whole universe with all its diverse content might be made of a small number of different kinds of things. There might be polyhedra, there might be elements like fire and water and things, but in any case, everything's made of a small number of things. And that was not an obvious observation, but one that came from antiquity. But in antiquity, there wasn't really a notion of, as I was saying before, of this kind of dynamics with time. Then in 1600s, there was kind of this idea of using mathematics to model the world, and a notion of time where time was a thing in a formula where you could just say, I'll pick my time and it will be this. Then in the early 1980s, I would say substantially through my efforts, kind of this idea of you can use programs as fundamental models of the natural world started to sort of come in, and that has different features in terms of time. For example, computational irreducibility is a common thing. You can run the program that represents your model, and you can explicitly run it and find out what it does, but you can't expect to jump ahead and say, oh, this is what's going to happen at this time without running through the steps. But that's sort of the next paradigm, is this kind of idea of the sort of computational paradigm where you're doing these things where you're sort of running programs to find out what's going to happen in the world. What has come up from our physics project is what I might call a multi-computational paradigm, where you don't have just sort of a single thread of time. You're not just looking at a program running. You're looking at something where you essentially have a program, but there are many possibilities at each step in the program. And you have this giant multi-way graph, as we call it, of possible histories that can occur. And then what you realize is even to know what's happened is not trivial, because you have this big collection of threads, of different threads of time, so to speak, different threads of history. And you have to basically have some notion of an observer to decide how it is that you're sampling this kind of multi-history kind of structure. And there's sort of a precursor of that idea that arises in relativity, again, actually, as we now understand it in quantum measurement. And again, that's kind of one of the core pieces of what we're now understanding with our physics project. And that methodology actually applies to a lot of fields other than physics. So that's kind of a piece, it's part of the story of sort of new methodology from our physics project. And I fully expect that there will be sort of a period of rapid growth, both in sort of what's possible in physics now and in what's possible in other fields by using the somewhat different modeling paradigm. And I think that's something where you can expect to see rapid growth and where it will look like, oh my gosh, things are changing at such a rapid rate. And gradually everything will be figured out there. And again, it will go into a long 100-year grind of making the next piece of progress, but we're still far away from that. So I think it's sort of an interesting thing that these fields always go through these cycles of, you know, new methodology, rapid growth, sort of once the easy stuff has been done, then a long grind until a new methodology is invented, and then things can start off again. And sometimes there are fields where just nobody cared about that before. The questions that were being asked, just nobody really cared. Like molecular biology is a good example, where, you know, people just weren't that interested in those aspects of biology, of looking at things at a molecular scale and so on. It became clear that was very important to understanding lots of things in biology, but that was kind of a new and different field. Similarly, computer science, another area where, you know, if you'd asked the early sort of mathematicians who were kind of buzzing around the early computing and so on, you know, is this going to be a whole field of endeavor of something to study? They wouldn't have said it was. I happened to, when I was at the Institute for Advanced Study in Princeton, some of the people who worked on von Neumann's computer project came back to talk about things, and some of the mathematicians who'd been there at the time when that project was happening in the 1950s were also still around. And there was kind of a bit of controversy, because the mathematicians, when von Neumann had died, had been very much of the, oh, there's this nasty computer thing off in this building, let's just get rid of all that equipment junk. You know, we just want to do math, which just requires pencil and paper. And Tom Watson, who was then CEO of IBM, kindly offered to send a truck to come and collect the equipment from the Institute to take it off to, I guess, New York City, where IBM's headquarters was at the time. And I think but in any case, the encounter between sort of the mathematicians and the people who'd worked on the von Neumann computer project, I guess I asked a bunch of questions in this somewhat public forum about, which sadly probably wasn't recorded because the answers were pretty interesting, about kind of, well, you know, what did you guys, mathematicians, really think would happen with computers back in the days of von Neumann? And there was quite a spirited discussion of whether they had anticipated anything significant from computers or not. But that was another place where kind of the question of computer science, so to speak, was there going to be something to study there? Now, in my own efforts in my big book, A New Kind of Science, and my kind of studies of the computational universe and studying what simple programs do, there's a big question of, is that a thing worth doing? Well, I think we have very good evidence now, and we have a few decades of work that have been done by people making use of the fruits of kind of the theoretical study of simple programs in the computational universe. Less has been done on that than should have been done. It's really a field at least as rich as pure mathematics. In fact, in some kind of definitional sense, it's vastly richer than pure mathematics, although probably less human than pure mathematics, less amenable to certain kinds of human reasoning than pure mathematics is, but nevertheless a vast and fertile field that has been much less explored than it should have been, because people have still not really understood as clearly as they should have done why one cares. Why is this, like pure mathematics, a thing that is worth studying, so to speak? And that's another issue in sort of the development of sciences, is people suddenly realize, oh, this is a thing worth studying. Let's go off and study it. I think we're seeing today, I think we can see some things with quantum computing, for example, where people had studied, including myself even, back 40 years ago and more, had studied aspects of sort of how would you bring quantum mechanics into sort of the idea of computing and Turing machines and all those kinds of things. And it was like, yeah, you could do that. But at the time, people thought physics is not like computing. People thought physics involves differential equations and real numbers and continua and things like that. And it's different from the story of physics. I didn't think that. I thought the two things were the same from the early 1980s. And at least I thought that. I didn't know about fundamental physics, how fundamental physics would correspond to computation, but I did know and had very good reasons to believe that kind of the overall mechanisms of physics, kind of the infrastructure of physics, was all about computation. It was not about mathematics. And that does seem to be what's playing out. But I think that the thing at the time, when one had talked about, like, say, quantum computing, it's like, well, there's the quantum stuff, that's physics, there's the computing stuff, that's computing, and they're not really connected. And so in more recent times, people have been very much trying to figure out, can we get quantum mechanical effects to do computing kinds of things? And it's kind of like, well, in the case of digital electronic computers, we have this one idea of semiconductors. It had been a previous idea of vacuum tubes before that. Sort of vacuum tubes were a way of doing computing. Then they've given way to semiconductor devices. Then are the things that we can use next things which somehow are more obviously quantum mechanical? And then can we potentially leverage effects which are quantum mechanical and not classical? I'm skeptical about that last thing, but the idea of using other kinds of foundations for computing that are, computing ultimately, computers are physical things, so ultimately the raw material is going to come from physics, but exactly whether that physics is ions in ion traps, or whether it's photons with various kinds of interference patterns, or whether it's superconducting interferometry devices with quantized magnetic fields and things. It's not clear which of these is the right kind of technology to use, but the fact that people have gotten interested in that in recent years is another one of this. This could have happened 30 years at least earlier than it did. And it's just because people weren't thinking about things in that same way, and so it didn't happen at that time. And I think there were a few, there were a few sort of stimulating kind of theoretical discoveries, but it still could have happened a lot earlier. Let's see. All right, I'm going to just take a few others. Parmenides asked, did I ever meet Howard Georgi and Shelley Glashow? Yes, I've known Howard Georgi, I would say fairly well for how long is it? 44 years, 45 years. Shelley Glashow, I see from time to time. I don't know him terribly well. Howard is always a person who is a very cheerful person, works at Harvard, and I know has done a lot of great stuff with Mathematica and our Wolfram language system in teaching physics at Harvard and so on, and doing research there. In fact, Howard is on my list of people who I should get into. I'm going to be starting a kind of series of interview Q&A sessions, which are really me trying to learn about things from other people. And Howard is somebody who's on my list to try and get to think about some sort of phenomenological consequences of our theory of physics, because he's good at that kind of stuff. And used to be fun talking to him about that when I was in that business back in the late 1970s. There's a question here. There's two questions here. There's a question from James. How did I get on with John Conway? Do I have stories about him? You know, John Conway, who sadly died last year, John Conway and I had many similar interests in terms of topics, but we were often interested in the same topic, but for utterly different reasons. I would say that John Conway was in some ways a pure mathematician who was very pure, and in some ways a very game-oriented mathematician who was very much into kind of the whimsical and the kind of exotic, so to speak. And I suppose my interests, we've both been interested in how systems that are defined by simple rules of various kinds, what those systems can do. I've been interested in that from a sort of scientific, almost natural science point of view, understanding the complexity those systems can produce. John Conway, I would say, is more interested in, well, what can we figure out kind of either as a, isn't that cute, or how can we make sort of a piece of pure mathematics out of these kinds of things? I remember the first time I met John Conway, and this is, I think, a story I can reasonably tell. Was probably 1980, between 1982 and 1984. I can't remember exactly when. It was at a conference in the south of France that was about automata theory and sort of theory of things like cellular automata, finite automata, those kinds of things. And I'm at this lunch with a bunch of mathematicians and John Conway. And John Conway is asking people, what are their dates of birth? And he's then using, then saying, oh, I can tell you what day of the week you were born. It's like, okay. And so he spends, I don't know, 15 minutes or something doing this, going around the table. I don't know, maybe it was a way of stealing people's personal information. I don't think it was. Eventually, I'm like, I just can't take this any longer. This is ridiculous. Why are we sitting here? This is a bunch of people who have all kinds of interesting things to discuss about sort of sophisticated math, and we're doing this party trick. And so anyway, the lunch ends, and kind of I'm going off with John Conway, and he's like, were people not impressed with that? And I'm like, no, that's just a party trick. You're a serious mathematician, and you've got much more interesting things to talk about than that crazy party trick. And I really don't think he got it. I really think that he didn't make much of a distinction between that kind of party trick and something about sort of the far reaches of number theory or group theory or whatever, which is very strange to me. But anyway, we had a long conversation walking around the cliffs around that site, talking about kind of things like undecidability in mathematics. He had a rather different point of view than mine about that, and about how common undecidability and universality would be in mathematical systems. But he worked on, he was much later, I was very interested in sort of the history of things like his game of life, cellular automaton. And I had a long phone conversation with him. Actually, I recorded that. And sometime I should put out the recording of it. It's I have lots of these historical recordings, and eventually I'm going to get around to organizing all of them and putting them out there. But the thing I was interested in there was, how did John Conway come to invent the game of life cellular automaton? And he's, there's a mythology about, oh, it was this game, it was based on the game of Go, et cetera, et cetera, et cetera. And I'm like, really? And so I pushed quite hard. And it took me like 2 hours of drilling. And eventually he was telling me, well, actually, he had just become he wanted to get a job in Cambridge. He'd really been a number theorist, but the only available job was in logic. And so he'd taken this job in logic, and he wanted to do something that was about logic. And so he got interested in the question of how could you enumerate the recursive functions. And he had also been reading stuff that people like Ulam had written about cellular automata, and et cetera, et cetera, et cetera. And I was saying to him, I just don't get it. You tell everybody you invented this as a game, but actually you invented this as a way to study infinite matrices, which is what Ulam had been interested in, and a way to enumerate the recursive functions. To me, that's a lot more interesting than the fact that you invented it as some kind of game. Well, it was different points of view for different people. I think then there's a real mystery about where the actual particular rules for the game of life came from, because I drilled John Conway for a long time about that, and he was remarkably evasive. And I think I suspect he did not come up with the actual rules, the specific detailed rules that became the most popular ones. Who cares? The idea, the context, as far as I'm concerned, is the most important thing. Once you're down to, well, let's enumerate possible rules, which one is going to be the most interesting one, that's an interesting thing to do, and it's a piece of the story, but you have to have the whole idea of setting the whole thing up in the first place. And I think in his kind of very pure mathematician way, it's like, well, if I didn't invent the particular rules, I shouldn't get credit for it. And he was very, very concerned about credit for things, very, very concerned about that, and had a tremendous habit of sort of trying to take things and sort of rename them to sort of attach himself to the whole enterprise. In any case, it was kind of a very funny conversation because it was like, well, who was involved in the early days of the game of life? And there was a person called Steve Bourne, who was in fact the person who invented the Bourne shell. If you use Unix, the SH shell is the Bourne shell. That's the same Steve Bourne as programmed the game of life on a PDP 6 or something. And then there was a person called Richard Guy, who died recently at the age of 100 and something, who was a kind of number theory and games person who was involved, and his son also was involved with discovering the glider in the game of life. And then anyway, then things went on from there. But the actual sort of early origin story is still a bit shrouded in mystery. And I've been planning actually to go and try and drill that some more. And there's a chap who I think was involved in it, who we did some sort of interviews a few years ago with some people who are involved in kind of discovering interesting behavior in the game of life, as sort of a model for how engineering progress can happen, and been meaning to piece together some more of that. Oh, there are all kinds of questions here about, I could tell you lots more about John Conway. I think I was, a woman named Siobhan Roberts wrote a good biography of him. I was quite amused because she kind of wanted to interview me about John Conway. And I think my first statement was, my relationship to your subject was complicated. And she quotes that line in her book and has a quite accurate and rather charming few pages about some more detailed description of my interactions with John Conway. But I would say that the most notable thing is that interest in some of the same topics, but just completely different motivations for being interested in them, and so on. So, well, we should probably wrap up here. I need to go off and do something else. There's a question about Carl Sagan here. I never met Carl Sagan, unfortunately, although for various reasons, I was very curious. Oh, how did this happen? Somehow from his widow, I got a copy of his CV, which is interesting mostly for being unbelievably thick. I think I was interested, I can't even remember why that happened. We were exchanging mail about something. And it's just interesting because I think Carl Sagan was a very committed kind of popularizer of science and really sort of played all of the venues. And his CV is just an amazing collection of different sorts of places and so on, where he was kind of taking the message of science and so on. Kind of interesting to see that. All right, I think we should wrap up here for today. So a bit of a romp through a variety of different topics. So we had a number of questions here that look like they'll be a good seed for next time. So thanks for joining.